What is going on, guys? Welcome back to a new video. Today we're going to be learning about hash maps. So moving on from the linear data structures, now it's time to focus on hash maps. Hash maps map keys to their related values and are one of the most efficient data structure when it comes to retrieving stored data. This is because the key is associated with every added value, allows faster retrieval later on. When you come across a coding problem that requires you to store and retrieve data, keep in mind that hash maps can often be the most efficient data structure for that scenario. Now, before I move on, I want to mention if you are enjoying this series, please subscribe, comment, and like. Appreciate you. Um, and also, if you're looking for jobs or internships, check out the first link in the description. But with that being said, let's move further along here. So the hash map methodology. Let me see. Let me go back here. Yeah. All right. So we'll look at tables first. So a data structure's main utility is relying for data to be represented in a way that resembles the way people will use that data. Now, in some cases, the primary function of that data will be sequenced through like a list. So we'll use a data structure that allows for easier iteration, like a linked list. In others, the usefulness comes from specifying interrelationships with the data. In the case of tabular data, here's a relationship between them. So each column corresponds to a different feature of the row. So let's consider the following table. Each state on the left corresponds with a state flower. New York has a state flower of rose. I didn't know that. That's crazy. I wonder what Texas is. But okay, so each state on the left corresponds to a state flower. For instance, New York corresponds to rose. This kind of table only has two columns, represents a special relationship in mathematics called a map. This table maps states to state flowers, but many other relationships can be modeled with maps. So for example, we have oceans compared by size, so we have ocean name, and then the size mapped to it. So it's basically like an ordered pair, if you will, in math. Now, being a map means relating two pieces of information, but a map also has one further requirement. Let's consider the following table. Miles Davis, we have Illinois, John Coltrane, we have North Carolina, and so forth. Now, in the above table, we map different jazz musicians to the state that they were born. While talking about a map, describe the inputs, which is jazz musicians in this case, as the keys of the map. And the output, here's the state of origin that is set to be the key, or the value at a given key. So these are the keys, these are the values. In order for a relationship to be a map, every key that is used can only have the key to a single value. In this example, every musician can only have one state that they were born in, so it works. There doesn't need to be a value for every possible key. There just can't be more than one value for a given key. For instance, Miles Davis can't be born in both Illinois or Kentucky. It can be one or the other, right? So if we looked at this relationship another way, with the states as the keys and jazz musicians born given state as the values, this would not be a map. So this is what it's trying to say basically. So keys have to be basically distinct, okay? These are the keys, right? So every map has a key and a value, okay? And these are the keys. So Miles Davis would be the key, and the value would be Illinois because that's the state of birth that he was given, okay? Now, they're saying that if you flip it, if you make these the keys, the state of birth the keys, and then the musician as the values, it wouldn't work because you have two different keys that are the same value. Like this wouldn't work at all. So that's why you can't ever make these the keys. These are always the values. The keys have to be distinct. They all have to be different. Okay. So moving on. So hash map methodology. In the case of a map between two things, we don't really care about the exact sequence of the data. We only care that a given input, when fed into the map, gives the accurate output. Developing a data structure that performs this is tricky because computers care much more about values than relationships. A computer doesn't really care to memorize the astrological signs of all our friends, so we need to trick the computer into caring. So you perform this trick by using a structure that the computer is already familiar with, an array. An array uses indices to keep track of values in memory, so we'll need a way to turning each key in our map to an index of our array. Imagine we want our computer to remember our good old friend Joanne McNeil in Libra. We'll take her name and we turn that name into a number. So let's say that the number we correspond with the name Joanne McNeil is 17. Find the 17th index of the array we're using and save the value Libra there. How did we get 17 though? Well, we use a special function that turns data like the string Joanne McNeil into a number. The function is called a hashing function or a hash function. Hashing functions are useful in many domains, but for our data structure, the most important aspect is that a hashing function returns an array index as output. Okay, so hash functions. Oh, can you interact with this? Oh, that's actually so cool. Okay, so a hash function takes a string or some other type of data as input and returns an array index as the output. In order for it to return an array index, our hash map implementation needs to know the size of our array. So if the array we are saving values only has 4 slots, our hash map hashing method should not return a bigger index than that. So in order for our hash map implementation to guarantee that it returns an index that fits into the underlying array, the hash function will first compute the value using some scoring metric. This is the hash value, the hash code, or just the hash. Our hash map implementation takes the hash value mod the size of the array. This guarantees that the value is returned by the hash function can be used as an index. A lot of terms here. So let me kind of explain this a little easier. So basically what happens is you have let's say 4 slots. Now the hash function, it's basically like a formula that you put in something. Let's say you put in the letter A. Okay, it knows that A is like the first letter of the alphabet. Let's say you have 4 slots. A will be put into the first slot. B will be put into the second slot. C will be put into the third slot. And D will be put into the fourth slot. Now, when it comes to E, right, it's the 5th element of the alphabet. You can't put it in the 5th slot because the 5th slot does not exist. So our hash function basically works in a way that it returns only 1 through 4. So it would return 1 if we're going like that, right? E would be put in here, F would be put in here, and so on and so forth. So the hash function is basically just a mathematic value like that. Okay, so array length is 10. So we'll do like, we'll do 4, okay? And we'll do like A. What if we change it to B and then C? and then D and E. Yeah, see? Y would be 1, J would be 4, like that, right? It's pretty cool, right? So the hash function is the main controller. Okay, cool. So how to write a hash function? You might be thinking at this point that we've glossed over every important aspect of a hash table. We've mentioned that a hash function is necessary, described some features of what a hash function does, but really never gave an implementation of the hash function. And that does not feel like a toy example, right? So part of this is because a hash function needs to be simple by design. Performing complex mathematical calculations that our hash table needs to compute every time it wants to assign or retrieve a value will significantly damage a performance of a hash table for two things that it should be able to do. Hash functions need to be able to take whatever types of data we want to use as keys. We only discuss strings, a very common use case, but it's possible to use numbers as hash table keys as well. A very common hash function for integers, for example, is to perform a modular operation on it to make sure that it's less than the size of the underlying array. If the integer is already small enough to be an index into the array, then there's nothing more to be done. Many hash functions implementations for strings take advantage of the fact that strings are represented internally as numerical data. Frequently, a hash function will perform shift of data bitwise, which is computationally simple for a computer to do, but can be predictably assign numbers to strings. In the application, change the key and watch how a hashing function might create a hash value. So we'll change this to, let's see, so this gives us the hash value, right? So we'll do code, and it gives us 411, right? And then let's say we give it hello, gives us 532, like that. It's pretty cool, right? So basic hash maps. So now that we have all the main ingredients for a hash map, let's put them all together. First, we need some sort of associated data that we're hoping to preserve. Next, second, we need an array of a fixed size to insert our data into. Lastly, we need a hash function that translates the keys of our array into indexes into the array. The store's location at the index given by a hash is called a hash bucket. Let's use the following example for our hash map. So we have album name, the Low End Theory, Midnight Marauders, Beats, and then this is the release year. So map here relates a Tribe Called Quest Studio albums with the year they were produced. We'll need an array of at least size 4 to contain all of these elements. Yep. And a way to turn each album into a name into the index into that array. For each album, we'll do number of lowercase a's in the album names plus the number of lowercase e's in an album name. So let's take that hash and calculate an array by performing hash value mod 4. So hash value mod 4 would just give us 2. Hash value mod 3 would give us 3. Hash value mod 4. So the 5 mod 4 is 1. 4 mod 4 is 0. So do you guys understand how we got this? So 2 is smaller than the mod 4. So it just stays as 2. 3 is smaller than 4, so it just stays here. 4 can go into 5 one time, so the remainder 1, so it's 1. And then 4 goes into 4 evenly, so it's 0. First, the key is translated into a hash using our hash function. Then our hash map performs modulo arithmetic to turn the hash value into an array index. So as we saw here, this is insane. So we'll do array length, we'll do 4, we'll do 4, and then we'll do a, and the value would be apple. And let's say we do B and C and D. It'll be like that. Now that's going to end it for part 1 of hash maps. Stay tuned for part 2. It's going to be the next video. But with that being said, thank you so much for watching, and I'll see you in the next one.